I'm extremely excited to see especially since we had one of these just last week and we're going to have another one next week. Heads up, which will also be cool. So I'm very excited to see lots of you here. My name is Ed Kazarian. For those of you who don't know me, I am the sort of coordinator of the Theorizing at Rowan series. It's my baby, if you want to put it that way. And we're very excited to have Professor Lund here to talk. I'm going to say a word or two about the series and just sort of how this is going to go, and then I'm going to introduce Professor Lund, and then I'm going to get out of the way and let him deliver his presentation. So for those of you who are not familiar with the series, Theorizing at Rowan is a series of work-in-progress lectures sponsored by the Philosophy and Religion Studies Department, which we've been doing now for 4 years. And these are work-in-progress lectures. The point of them is in the first place to sort of foster scholarly exchange among members of our department and also between our department and the rest of the university. And also we bring in scholars from outside of Rowan, so that kind of circulates things in even wider circles in ways that have been very productive and interesting for all of us. Another part of the point of this, and this is for those of you who are students, is to give our students a chance to hear and engage with us and other scholars who we invite about their current ongoing research in philosophy, religion studies, and other related fields, right? So we want people to have a chance to actually engage with people working on current research, about current research. This is not just a dead body of knowledge. It's very much a living one. And an important part of your experience as students here should be to actually kind of participate in the production of new knowledge. So with that in mind, you should feel very free when we get to the Q&A after Professor Lund's talk to sort of jump in, engage, ask questions, and so on and so forth. Everybody's going to be invited to do that. So with that said, let me introduce our speaker very quickly. Professor Matthew Lund has his PhD from the University of Illinois at Chicago in 2004. He has taught at Rowan since then. He has a book on Norwood Russell Hanson, called Observation, Discovery, and Scientific Change. He's been working on reissues of posthumous volumes and re-editing of posthumous volumes in Hanson's from the 1960s and 70s. And he's also sort of moving away from the Hanson stuff. He's been doing a lot of work on Hanson for a while into history of philosophy of science more generally and epistemology. He's been teaching in all those areas at Rowan. So lots of stuff here, and this is some of that movement is caught up in the talk that he's going to give tonight, which is entitled Bessel and the Personal Equation: The Epistemic Consequences of Perceptual Relativity. And I'd like you all to join me in welcoming Professor Lund.
All right. Well, thank you so much. I appreciate having such a good audience. Hopefully, I'll be worthy of it. I don't think I will be, but anyway, I wanted to just sort of preface my talk by explaining a little bit how I got interested in it and sort of how everything changed as I started researching it more. This idea of the personal equation sort of occurs in lots of different narratives, mainly in experimental psychology. And folks will mention it and they'll say, there was once this weird sort of problem, and then some people sat down and they kind of looked at the data and they figured it out. And it's really nice because if there are little perceptual differences, we sort of have an equation that adjusts all of this, and it's not a big deal. Don't worry about it, nothing to see here historically. And so that's sort of how I got into it. And then I started reading more and more about it, and I found that my philosophical presentation might be abridged because I think the historical presentation is so interesting that just trying to understand exactly what happened, how it happened, why it happened, takes a bit of unpacking, and then the philosophical lessons might be a little shorter than I had envisaged when I started. Okay, so the astute reader, if they had seen my abstract, they'll notice that it's subtly changed in some ways, so I'll read it to you. It says in 1796. It used to say in 1795. I had to correct myself, and I'll explain why I did that. It's not an obvious thing. It's not just a purely stupid mistake. There's a good reason for it. The Astronomer Royal Nevil Maskelyne fired his assistant for, quote, observing the times of the transits too late. In 1823, Friedrich Wilhelm Bessel analyzed the Royal Observatory's data and came to a startling conclusion. Different observers of astronomical phenomena detect transits with what he called involuntary constant differences in the times of the observed events. This conclusion eventually led to the idea of the personal equation. This gets developed later. In one of my slides, I'll kind of give you a timeline of when all these different concepts emerge historically for observers, and spurred psychological investigations into the processes of visual perception and put observational astronomy back on an objective footing. Usually that's meant that psychology did that. Now I'm meaning it to say, actually just the way of sort of handling this in a quiet way that Bessel handled is what got it back on an objective footing. Okay, and so I'm going to try to get into as much as one can of the original sort of discovery process and reasoning that Bessel had engaged in back in the 18 teens through the 1820s. Okay? All right, so I have here a typical quote from John Herschel, the astronomer from the 1830s, and this was expressing sort of how astronomers and scientists generally were starting to get sort of worried about the condition of the observer. So Herschel said, "Human hands or machines never formed a circle, drew a straight line, or erected a perpendicular, nor even placed an instrument in perfect adjustment, unless accidentally, and then only during an instant of time." You can see here a sort of a consciousness that the observer is entering the equation as one of the variables, and maybe people are a little bit worried about all of this, okay? So the way I'll break my talk down is first I'll give you some history. I call it the astronomer's apprentice. This is about David Kinnebrook, who was the assistant to Neville Maskelyne, who ended up getting fired for, as we might now say, just observing things differently than his boss. And of course, as is typical of bosses, he was very chauvinistic and thought any deviations from his perfect example had to be mistakes, and so he fired poor Kinnebrook. So after we go through that, I'm going to get into how Bessel's investigations proceeded. And they don't exactly proceed along this nice, clear, linear path in the way that I was just presenting things. And so this might take a little of that. Then I'll talk only very briefly about the thing that later came to be known as the personal equation, which had very important consequences within astronomy. Also, in many other fields, the notion of the personal equation was sort of absorbed, sometimes in really absurd and maybe even offensive ways. If I get a chance, I'll talk about what those were at the end. Offensive things are always at least interesting, but I won't talk about them now. They're not that relevant. And then at the very end, I'm going to pose a few very simple-minded epistemic questions that we can look at relating to this story and what kind of a lesson it might prove for us. Okay, so our story starts with Neville Maskelyne. He was an Astronomer Royal. There were only 10 Astronomers Royal during the time that Greenwich was an active observatory. And Maskelyne was the Astronomer Royal for quite a period of time, from 1765 to 1811. If any of you have read Davis Sobel's book Longitude, you'll know that Mascaline is sort of the bad guy in that book. What was happening was John Harrison was trying to develop this very accurate chronometer. We would just call it a clock or a watch. And Mascaline didn't like the way he was going about it. He didn't like his technological approaches. He even wrote into English law, he writes Harrison's name as providing a type of technology that will not be allowed for winning the Longitude Prize. So he certainly was nasty in this particular connection. But one of the things he was very notable for was improving the accuracy of transit observations. To us now, we might think of astronomy as just, something you have at a university as a subject. You have maybe an observatory, people look at stuff, they look at the moon. We might think of it as just being a kind of a novel, sort of a pastime. But of course, back in these days, astronomy was critically important because navigation depended on it, your commerce depended on it. And so this was the reason why many of the nations in Europe had observatories. They were maintaining them. They were trying to get everything to fit together nicely. So just keeping the time was a very important concern. In fact, the Royal Observatory had, for many years, they had an agent who would go out through London with his very accurate clock, and he would have people synchronize clocks. And then later they put a ball on top of the observatory that would drop at 1 p.m. that everybody could just look up at and sync their watches to. So this was a very important practical concern of the day. And during Mascaline's period running the observatory, he increased the staff at Greenwich, and that's an important part of the story. So the next slide, this is Mascaline's observing suit. And you might think I'm showing you this just because of its importance as an item of fashion. And that's not entirely it. It reveals quite a bit. This is from the Royal Observatory's website. And this was a fairly expensive item. It was made of Indian silk, and it was very well worn because Mascaline was freezing much of the year while he was sitting there trying to make observations. This was from a period when the Astronomer Royal did a lot of the observing. Maybe he got tired of this, and he started hiring assistants. And once he started hiring assistants, then little idiosyncratic personal habits will reveal themselves if they exist, and that's precisely what happened in the case of Kinnebrook. And so I should say too that the arrangements socially at the observatory were sort of interesting. So Mescaline and his family lived in the observatory, and Kinnebrook lived in a little side room. And at one point he was asked whether he wanted to take meals with the Mascaline family, and he wasn't sure what to do. And so he decided that he would take his meals back to his room with him, which kind of offended Mascaline. Mascaline also was trying to marry Kinnebrook off to apparently a widow, a person by the name of Mrs. Wilkinson, so I assume that bigamy laws were in full force back in these days in England. And Kinnebrook didn't want anything to do with it. And that was actually, chronologically, the event that most closely preceded his firing. So that's also interesting. A lot of this information wasn't revealed until the 90s when people started reading Kinnebrook's letters to his father. Okay, so this is the firing. This is the awful tidings that came to Kinnebrook. And this is listed in a report. Again, I say the actual date of the firing is a little tough to place because the report was summarizing observations from 1787 to 1798. But he says in this particular section that he thinks it's necessary to mention that Kinnebrook, who had observed the transits of the stars and planets very well, in agreement with me, all the year 1794 and for the great part of the present year, began from the beginning of August last to set them down half a second of time later than he should do, according to my observations. And in January of the succeeding year, 1796, he increased his error to 0.8 of a second. As he had unfortunately continued a considerable time in this error before I noticed it, and it did not seem to me likely ever to get over it and return to a right method of observing, therefore, though with reluctance, as he was a diligent and useful assistant to me in other respects, I parted with him. So this is his explanation of what happened. Now, I should explain exactly what these observations look like. And I think it would be difficult for me to characterize it fully on the PowerPoint, so I'm going to draw a little bit of this. But this is actually not the one from the Royal Observatory. This is Römer's transit telescope. And the idea of it is, as you can see, it's fixed on a sort of a vertical axis. And what one does is one has that telescope trained on the meridian for the observatory. And all these various observatories throughout Europe had their own special meridian. Okay? And actually the one at the Royal Observatory has been moved. And so the current location of the telescope is actually about 20 feet from where the meridian is and so forth. So this was always a sort of a practical problem. And what one would do is one would look up through the telescope and one would find a certain star any kind of celestial object would be referred to as a star. And once one got it in the telescope, there were these spider wires inside the telescope. So if you imagine it looking like this, the telescope that Mascaline and Kinnebrook were using had 5 of these spider wires. And so at some point you might see the star here, and at another point you might see it here, and at another point you might see it there. Okay? And now imagine what things are like in 1796. Stopwatches are not very good. You don't have the ability to take a photograph of any of this stuff. So how do you note the position with any kind of accuracy? So this is a real problem of measurement. So what the observers would do is they had a big pendulum clock, and this process for an equatorial star could take about 3 minutes, given the magnification of the telescope. What they would do is they would note the position of the star, and then they would listen for the tolling of the pendulum clock. And they would try to remember, okay, so where was it relative to this wire when I heard the pendulum? And you would have to remember this. There were also problems with magnification of the star, with weather conditions. Some people said, you should do it when the star is right in the center of the wire. Some people said it was right as it gets to the wire. And you can see why this would actually be a fairly complicated kind of process. It's also absolutely individual. So if I'm looking through this telescope, no one else can be looking at it at that same time. And so it's not a matter where you could sit down and do the Pepsi challenge and have both people look at the same time and figure out what's going on. You had to extrapolate back from these observations to figure out that there was a problem. Okay, so the method, this method is due to James Bradley, who was the Astronomer Royal preceding Maskelyne. There was a guy who didn't live very long between the two. And what he said he would do is he would try to mark out, like say he would hear the toll of the pendulum, and he would consider this something like 0.7. And then he would hear it again, and he might consider that at 0.2. And what he would do is he would average the position relative to this wire, which was your central wire. So you had a lot of different observations, and you could reduce those down to a single one. So this wasn't just a matter of a bunch of yokels, looking through a telescope and guessing at where this thing was crossing the wire. They had a very precise sort of method, and it was important that everybody shared the same one. Okay, so as I mentioned earlier, these transit measurements were critical for navigation. When Mascaline became aware that Kinnebrook's observations differed from his, they differed from a half second to 0.8 of a second. And if this was at the equator, this would compute to a 1/4 mile of longitude. So this would be a degree of error that nobody would have expected. Also at this time, we'll find when we talk about Bessel, that most of the observers believe that if you had a proper sort of method of observation, if you had the right kind of training, the right kind of seriousness about your task, and you would focus your attention, that would ensure an accurate measurement. So this was sort of a dominant belief. And of course, because Mascaline was so much more eminent than Kinnebrook, it was obvious to him that Kinnebrook was the culprit in this whole story. Okay, and here I have this is from the same report about the firing of Kinnebrook, where Mascaline talks about the method and sort of how precise it might be and what some of the variables are that might interfere with accuracy. So he says, though we cannot observe certainly to 1/10 of a second of time, we shall rarely commit an error of 2/10. But the mean of all the 5 wires, or of the central wire, and any pair of wires equidistant from them, may be expected to approximate still more to the truth. So he says, I can't be more wrong than about 2/10 of a second per wire, but if I have all of these together and I'm averaging them, how could I go this wrong? The great thing is to aim always at the truth. I think we can all agree with that. And avoid any partial method of observing, either an excess or defect, that our errors may not have a tendency to fall constantly one way. and then the independent observations of two observers will have a better chance of agreeing together and with the truth. The difficulty of attaining the desired exactness arises from various causes, sometimes from the great faintness of the object, sometimes from its over-brightness, a tremor or undulation, owing to a bad state of the air, or the quick motion of the star through the field of the telescope, occasioned by the great magnifying power, and sometimes from flying clouds. So he goes on, and he lists a lot of complications to the observation, much more than he would need to, because it's clear that he's maybe a little worried, maybe one could psychologize that he might have prematurely gotten rid of Kinnebrook. Later in his life, Mascaline actually hired Kinnebrook to do a bunch of bookkeeping and stuff for him. So he kept a relationship with him. Unfortunately for history, Kinnebrook died at about the age of 30 in 1802. And so nobody knows what he made of this episode. Had he lived another 20 years till he was a ripe 50 years old or so, he might have been able to comment on what exactly had happened, but he died and that was the end of it. Okay, and so I'll go back a little bit historically to talk about James Bradley. So Bradley was an Astronomer Royal also for a considerable period of time, and he developed what was called the eye and ear method. This is the method that I just presented. So you'd look at the clock, you'd get the exact minute and the second, and then you would mark out in your mind's eye, because you couldn't write it down on paper, where these various positions of the star would be at the tolling of the clock, and then you would sort of reproduce it later. So he developed that method. And when Bessel was young, one of the great things Bessel did was he came up with a reduction for Halley's Comet that really impressed Christian Olbers. And this is what got him his position academically. He was from a merchant's family, so he had to choose the poverty-stricken path of a scientist over being a merchant. And one of the very first things he did after that was he did what was called a reduction of Bradley's Greenwich observations. So what this consisted in was he was taking all of this raw data that Bradley had computed, and he was trying to reduce the errors out and try and give a full theoretical account of how all these various stars are moving. And Bessel was famous for having mapped thousands and thousands of stars and so forth in the process of doing this. So that was probably the first step that Bessel had in sort of getting deep into the observational minutiae of Greenwich, okay? All right, so now I'm going to change the subject radically. So we all know that it's the 7th game of the World Series tonight, and so I thought it'd be good to talk about baseball for a little while. This is actually a photo from a New York Times story in 2001, and it was a whole story about umpiring in baseball and all the various problems that you could have. And you might think that the umpire can look and see when the runner's foot touches the base and also see when the ball enters the glove, and all of this is happening extremely fast. And it turns out that the umpires don't do it that way. Primarily they listen for the repercussion of the ball in the glove and look at the foot. Sometimes they hear the foot and the sound of the ball hitting the glove. And lots of first basemen, for example, in this an article in the New York Times, Keith Hernandez talks about various ways first basemen would try to fool the umpire into thinking that they actually made the play when they didn't. So this is not just about baseball, but you know, the idea here, the old slogan is I calls them as I sees them. You know, I'm just using my eyes to make all these various calls. And Mascaline had a comment in this same report. He says, a good ear seems, in this kind of observation, to be almost as useful as a good eye. You have to coordinate these various senses together. So you might say it's I calls them as I hears them in this particular case. And to understand why the Kinnebrook affair was so sort of unusual, could we imagine a first base umpire who recorded the runner's foot hitting the bag a half second to 0.8 seconds too late? He would be fired. There'd be a lot of ugly confrontations out at first base if people were this imprecise. So baseball could not survive a variability of this kind. I don't know if anyone's ever tried to gauge the personal equations of baseball umpires? This would be an interesting question. The article I read came close to this because there was a perfect game in 2000 that was marred by an obviously blown call at first base, and it was due to the pitcher having tossed the ball, and the umpire said later he couldn't actually hear the sound well enough and he got confused and screwed it all up. Well, I don't think he confessed it that directly, but this is what people claimed had happened. So at the same time, it would have been very easy to forget Kinnebrook, and in fact he was forgotten for a long time. I should say there's an article in Nature in 1996 by a couple of Cambridge psychologists, and they went and looked back at Kinnebrook's data, and they found that he had an intense dislike for 0.1 and for 0.6. These numbers almost never occur in his observations. And this phenomenon was known in the 1880s when E.C. Sanford wrote about the personal equation, that when people make these estimations, there'll be certain numbers that they really don't like. And they just don't show up. So they have a little histogram showing the various endings of numbers. Similar things were done by R.A. Fisher in the 1920s about Gregor Mendel's supposed observations for his pea plants and inheritance, that they didn't show the proper amount of statistical variation, and that he probably fudged a lot of the data, which is interesting. So this is a similar kind of story to that. They also showed that his observations actually did get progressively more sloppy over time because of some of the rates of variability. So there might have been actually some substance to Kinnebrook having been let go. Okay. All right, so now I'm going to give you a little timeline of a lot of things that were happening in the late 18th, early 19th century. So the first one on the list, John Dalton's first description of color blindness, I find sort of fascinating. We all think of color blindness as a kind of an ordinary visual anomaly. In most of the Romance languages, the term for color blindness is some version of Dalton's name. Like in Spanish, it's daltonico. And so this shows where that came from. So it's kind of amazing that only then did he discover this. He discovered it because sort of pinkish compounds and greenish ones that other people said they could routinely distinguish, he could not. And his brother couldn't either, because they both had the same genetic makeup. I believe he was a protenope in terms of the type of color blindness he had. They exhumed his corpse and did some genetic testing on him and figured out exactly how he was colorblind. So that's interesting. Then, just 2 years later, Kinnebrook gets fired. Then in 1823, after about 8 years of work on the problem, Bessel notes in a report what he called involuntary constant differences in these transit observations. Then later, John Pond, who was Astronomer Royal, coined the expression personal equation in 1833. George Biddle Airy, who was the succeeding Astronomer Royal, who was a very important Astronomer Royal, started publishing personal equations as separate columns in astronomical tables in 1838. And then only much later, we get discussions of reaction time with the Viennese psychologist Zygmunt Exner, called Reflexzeit auf Deutsch. You also had a tradition with Wilhelm Wundt and Helmholtz, where they were trying to measure the speeds at which nervous transmissions happened. Helmholtz, especially with frogs. People were concerned even with how fast thoughts took to take place. One of these ridiculous notions was that reaction time was actually race-based, because the more Caucasian you were, the longer it took you to react because you had so much cognitive machinery working and so forth. So there are lots of ridiculous examples of that sort of thing. I'm indebted to a book by Jimena Canales called 1/10 of a Second for a lot of these things that I'm not going to talk about, but they're funny curiosities from the 19th century. Okay. A typical way this story is told, though, a standard way it's told, is that empirical psychology kind of came in And it rescued astronomy from what I call a relativistic quagmire. So people might have been worried, like, why am I seeing things differently than somebody else? And then psychology can come in and say, well, there's this kind of propagation delay in your perceptual system, and it's characteristic for each person, and we can measure this to some degree. And this was put forth by Erwin Boring in 1929, and it sort of became a default sort of story. Lots of people disagree with this story. I'm not the first to disagree with it. And what I'm going to argue in the remainder of my talk is that astronomy found its own way of dealing with these differences, and this synthesis with empirical psychology wasn't important to this astronomical story, at least in the 19th century. Okay, so now we'll turn to Friedrich Wilhelm Bessel. He was a very important mathematician and astronomer. I mentioned earlier that he came from a sort of a mercantile background, and he got into astronomy to the sort of horror of his parents. He was known as the first person to do a successful measure of stellar parallax. So one of the reasons the ancient Greeks, even though they had heliocentric theories of the cosmos, didn't go for them was because they thought we should see all of the celestial objects changing position relative to one another throughout the year if the Earth is indeed moving. And Bessel was the first person to provide a measurement of this. And this is important because this allowed you to measure interstellar distances. So it's very important, this sort of technological, theoretical discovery. He developed a very influential system of astronomic reductions, ways of taking data and forming that into sort of a more clean model. He also was one of the scientists who had an early hunch that the perturbations, as we now call them, in the Uranian orbit might be due to a distant planet, but he got ill and he ended up dying actually in 1846, the very year that Neptune was discovered. He oversaw the construction and operation of the Königsberg Observatory, and he also was involved and was a correspondent with Carl Gauss in coming up with a sort of a theory for error analysis. And I'll talk a little bit more about that as we go forward. Okay, so here are a few sort of historical questions. You know, how did Bessel come to discover that the differences between Mascaline and Kinnebrook were not due to sloppiness, arbitrariness? They were actually sort of repeatable sorts of differences between their observations. How did he get to that place? How did he make it from thinking that observation is just a matter of a well-trained, disciplined practitioner seeing the world as it is, to making this sort of qualification? And then we'll talk about this at the end, but was his way of resolving all of this rational? And we might ask, should he have been more concerned about what this might mean in terms of psychology, physiology, all the rest? Didn't seem to care too much about that. Okay, so here I'll just give you a quick sort of rundown of the history. So when Bessel finished his reductions of Bradley's data, he had read sort of a 50-page history of the Greenwich Observatory written by von Lindenau, a contemporary astronomer and friend of Bessel's, and he requested from the Bureau of Longitudes the data that Mascaline and Kinnebrook had. I mentioned earlier that the Germans in particular were very obsessed with error analysis. One of the great exemplary applications of error analysis came with Carl Gauss. He was able to use a bunch of Italian observations of a celestial object and reduce them using his method of least squares to find the actual orbit of this thing, and he said it was the planet Ceres, and so this was a shocking sort of demonstration. So the idea in statistics, you'll come across this sort of idea, though they even call the curve a Gaussian, and the idea is that it sort of has a center, and what he did was he would use the square, the difference from this mean, and reduce certain values. And he was able to reduce again what the data was for this Sirian orbit, so that he found what looked like a nice planetary orbit. More to say about Gauss in a minute. The idea that Bessel had was he wanted to find sources of error outside the limits of probability. He wasn't really concerned with things that a probabilistic approach could filter out. He wanted to know about errors that couldn't be contained in this way. So he lists early on what physical sources of error might be that could account for these differences between, say, Kinnebrook and Mascaline. So he says that maybe it's the magnification of the telescope, maybe it's the speed, or we might say the declination of the transit. So if the star is moving sort of across the field, from the bottom to the top, also you're going to have a different speed of transmission or transit. There was also a belief in the early 19th century that the bigger the instrument was, the more accurate it was. This was a belief that was true in the late 16th and early 17th century with Tycho Brahe. He had huge instruments and he was able to measure things thousands of times more accurate than anybody else did because he had a higher resolution form of instrumentation. He also wondered whether there were temperature variations throughout the day or maybe periodic differences through the seasons or where the Earth was in its rotation around the sun that might account for these things. So these are some of the things he thought about along the way. And I should mention sort of what there was an event that was kind of a false alarm with the astronomer Encke, and he had noticed some abnormalities in transits for Polaris when he was installing a new telescope at his observatory. And this was really the first thing that seemed to get people worried, and it turned out it was just due to a simple recording mistake. So it was nothing in the end. But in this exchange, Bessel starts to sort of conceive of the idea of an individual sort of physiological, psychological difference. So this is the quote from a letter he wrote to Encke in 1819. A constant difference, that is to say one which remains the same for all seasons, would have to originate from the observer who observes the passage of the star over the wire, either too late or too early. Indeed, I believe in the possibility of this error, and then he goes on to say why he doesn't think it's really a problem. He says, nonetheless, I believe that the observer is able to control himself so much that he can estimate the transits correctly. The emphases here are his. At least I have taken great pains to get into the habit of a practice which I consider to be free of this error. So he sort of, this is the first time he published the idea that he thought maybe this was internal to the observer, but then he quickly rejects it with the standard line on how observations work. Then in this historical record, there's a sort of a curious event in June, actually on the 26th of June in 1819, Bessel, von Lindenau, and Encke get together at the Seeberg Observatory, which Encke ran, and they recorded transits and they noted the initials of the people recording. And there was an indication that they would keep doing more of this, but then they had bad weather and they stopped it. And he mentions these observations in 1823, but doesn't say why they were doing them or what their motivation was at all. And then the most interesting part of the story begins in the winter of 1820 to 21. A young astronomer is recommended by Struve to come and see Bessel. And the letter says, I know this guy, he's very talented, but he could really use the expertise of somebody like yourself or something like that. So he kind of implies that Bessel is going to really be beneficial for Walbach when he comes. And as they're doing observations, they start alternating transit observations. They do this for several months. And so the way that this would work is you would have one person observe in the morning and then at night, and then the other person would observe that same object. And if you did this over a long period of time, you'd be able to see all the differences in the transits. So that the differences would effectively be doubled by this method. And Bessel noted that they had this sort of stable difference of 1.041 seconds, an astonishingly long amount of time over lots of observations. And then Wahlbeck was returning to Finland, and Struve had his observatory in Dorpat, which is in present-day Estonia, so he stopped off, and they did some transit observations also. And they noticed that Wahlbeck was, the slowest of the three, and he was, sorry, that should say 0.2, not 2 point. He was 0.2 to 0.3 seconds later than Struve. And maybe none of this would have mattered too much, but then Bessel remembered that in 1820 he and Struve had been doing some transit observations, and he hadn't thought much of it, and he looked at it and he found that their difference was 0.7. And what was interesting about this was this seemed to be a transitivity of the delay. You could take the difference between Bessel and Wahlbeck and then subtract 0.2 or 0.3 from it, and you get the difference between Bessel and Struve. So this was an interesting result, and this was what propelled him to want to let others know about what he had come up with. Okay, so this is another interesting part of the history. So Bessel presented his findings in a 7-page report in 1823. Interestingly, in the years 1875 and 76, when his sort of collected works were being edited, the editor decided to give that piece a title. And the title is Persönliche Gleichung bei Durchgang Beobachtungen, which means personal equation in transit observations. Okay, completely anachronistic because he was not talking about anything like a personal equation back in 1823. Didn't give it a title, it was just a report. So that's interesting. So that may be one of the reasons why people think of Bessel as having discovered the personal equation. However, interestingly, the comparisons were not as replicable as one would have hoped. Struve did a bunch of joint transit observations with Argelander, another astronomer, and they never were able to note stable differences between the two of them. Also, Bessel investigated covering observations and uncovering observations of eclipses. There was no involuntary constant difference phenomenon surrounding those observations for some reason. So that made it a little bit weird. And also, from year to year, the difference between any two individuals would sort of drift and change. And so this was not a stable, predictable, transitive, replicable phenomenon, as it turns out. Didn't quite work as nicely as it might have appeared. Carl Gauss, when he saw Bessel's report, just said, well, this Wahlbeck guy is just a bad observer. He's just sloppy. And he left it at that, didn't want to get any deeper. Christoph Hoffmann wrote an article in 2007 that a lot of my talk is indebted to. Talks about how there were actually very few published notices of Bessel's findings or his discovery. Almost nobody really commented about it. And so Hoffmann has a nice synopsis. He says, a few footnotes, a new column added to the tables of observations, and 2 or 3 sentences are all that testify to the initial reaction to Bessel's findings. And Hoffmann characterizes this as what he calls a cold tradition. What happened was, after Bessel's report, the practice in astronomy was subtly changed. You didn't want to mix transit observations between different individuals, so you tried to keep the same people doing the same types of observations. You would record the observer's initials so that you knew who made the observation. And so I would characterize this that the problem was kind of controlled, it was contained, but it wasn't eliminated. It was just sort of something that you had a little practical sort of heuristic that you could use to work around it, and that was good enough for the purpose. As Hoffmann puts it, these practices were necessary to keep the problem undiscussable, sort of put on the margins and left alone, and nobody needs to worry about this. And I should mention, astronomy is an interestingly historical science. We know when one of Alexander the Great's battles happened in the Indus Valley because they talked about a total eclipse of the sun that happened there. And so we can date these things. Ancient data in astronomy is still useful. It's a historical science. And so you really didn't want to reject observations. If you could possibly keep them, if you could hedge them somehow, if you could qualify them, then this was what you wanted to do. And this is a very old tradition within astronomy. So as I say here, he sort of demonstrated a phenomenon, the existence of a phenomenon, but it was a bit equivocal, and it wasn't trustworthy enough to allow you to normalize observations. What I mean by that is if I were to do an observation, I could compute what your observation would be. And then later we could actually just have a fully objective kind of observation. This is something you get in the 1850s. There was no potential for that in the 1820s. A little bit more of the history, and I'm getting very near the end, so don't get impatient with me. I'm going to stop talking soon. In 1840, astronomical observations began publishing personal equations, and this became a standard practice across Europe, that you'd list a bunch of observations, you'd list the observers, and you'd list their personal equation, show how off they were from some mean value. There were also technological advances. Actually, in the 1820s, there was a German scientist who developed this little sort of a wheel that had paper on it. And the idea was this would keep rolling, and when you looked up and you saw the star across the wire, you would just have a little key and you'd put a little etching on it, and you'd be able to tell exactly when this had happened. But it turned out he wasn't very good at ensuring that the paper was tracked consistently, and it's because the paper would slip, so it didn't work very well. In the 1850s, that same kind of technology was developed at Harvard, and this was called the American system of chronometry. And basically what happened was you had this big drum, and you had little 1-second intervals that were being written on it with a pen, and then when you saw what you took to be the transit, you'd push a little button and it would make a big spike. And this effectively got rid of the personal equation. It got filtered out. Maybe more interestingly, Francois Arago maybe could be credited as having first noticed the involuntary difference problem in the first decade of the 19th century. In the 1840s, he came up with a method where he had an observer look in the telescope, and then as soon as he saw the transit, he would put his hand up, and he had two people behind him keeping time. And it turned out that that method was also very much more resistant to personal equation effects. But it was forgotten because the galvanic chronometer came later. Interestingly, even into the 1930s, sets of observations would still publish personal equations for the observers, even though actual naked or telescopic personal observations had been done away with for almost 40 years. So it still retained a sort of life, even though the reasons for it were gone. Okay. I should say too that this was still a glaring problem until the end of the 19th century because the galvanic chronometers were so expensive that lots of people still use the eye and ear method to the end of that century. Okay, so here's my kind of lesson. This would be my thesis I'm arguing for, that astronomical data and practice were precious commodities. And Bessel had believed that timing differences were due to, as he writes this in a letter to Gauss, due to the switching between sensory modalities. Switching from hearing to vision and back again was what caused the problem. But he really wasn't concerned with psychological diagnosis. He only wanted to supplement astronomy with a minimal epistemic account of observation so the historical practices of astronomy could be preserved and extended. The observer as instrument silently enters the picture. So you don't want to ruffle anybody's feathers with these ideas, and he was very successful at that. Okay, so then I have some little questions, discussion type questions that we might talk about, but we can talk about anything. What should we make of cases of perceptual relativity? This is an old kind of philosophical problem. You know, what if all the colors I see are the inverse of yours? You know, what are we going to do about that? Is that really a problem we should worry about? If there are these perceptual relativistic problems, wouldn't they express themselves in some kind of difference in practice or difference in beliefs about the world that we could test? And I could also ask, was the way that Bessel identified the constant and voluntary differences, was this really in advance, or was this just kind of a sloppy means of salvaging the data however he possibly could? And I think the other question we might all think about is, are there still substantial ways in which personal differences can affect scientific practice now, or I suppose even outside of scientific practice? Okay? All right. Thank you.
So do you want me to moderate, or do you want to just field your own questions?
Why don't you do it, because I feel like...
What I will do is, I'll moderate, and I'll also bring the,
Okay.
the microphone around, because we need to do that. So who's got... Patrick, you want to start us off? All right.
It's always the case. So it seems that at least in this case we've examined for Bessel, that it seems that this perceptual relativity problem seems related to the fact that people are really bad about estimating how far things are between things, which is something that, psychologically we've known people are absolutely horrible about perceiving distances visually for as pretty much as long as we've been studying visual perception, and that it seems that I'm not certain how much I'm alarmed by this idea of perceptual relativity, and it seems like we control it in all these other areas, and it just seemed we had this one method that seemed heavily reliant on something we know we're bad at. And then we were bad at it.
Yeah, I mean, I'm not sure if I'm getting what your question is entirely, but I'll speak to a... Well, go ahead.
Yeah, I guess my question is then, it seems that this kind of asking questions about the perceptual relativity, it seems that we just end up with, at least this example, it seems entirely unconcerning that it seems that, at least on the basis of this example alone, we had a method where we relied on our ability to do something we know we aren't very good at, and then we weren't very good at it.
Well, I think I would qualify that and say people discovered that they weren't very good at this method, that it seemed everybody would do the same way. And I guess one way to think about it is, it's not just that Kinnebrook was making arbitrary mistakes. It was that the way he was perceiving all of this was regular enough that it would depart from what Mascaline was doing by a certain amount. So it would look to him as though it was crossing the wire at this specific moment, even though it would look to Mascaline like it was crossing at a different moment. So in terms of the phenomenology of the experience for both people, it seems that it would have been different. I think that's the part that's kind of shocking about it. It wasn't just an error, it was actually part of the experience they had as they were looking. Does that answer your question?
Well, it seems, at least if we're using the visual center of the object, that what you would end up with is, we know people are really bad at perceiving where the actual centers of objects are, and they have consistent variances from that based off of where they perceive visual centers, which doesn't seem to be something like a direct perception. It's something I'm more trying to infer based off of the shape of the object. And I'm supposed to say, I'm bad at doing those kinds of inferences because I'm bad at inferring where midpoints are for lines and things. So it's, okay, I relied on my ability to do those kinds of estimations. I know I'm bad at those kinds of estimations. I ended up with errors.
Right. We know this now, although there was a lot of research in the 19th century about those kinds of errors, what is called co-elimination errors, where you would identify a different part of the line as the center from somebody else that were also things that people called personal equation effects because they differed from individual to individual. But that wasn't known at this time. So we might have the benefit of hindsight for some of that. So I think David has a...
Yeah, David's next. Okay.
So I may have missed this, being a little drowsy, but with the personal equations, what was then done with the data? Did people average the different measurements so that they ended up with data? Did they just publish all the different ones with a personal equation with each person's thing and let people do what they wanted to establish data that everybody could work with? And second part of the question, when other means of measuring transit arrived, has there been a process of going back to this previous data and somehow calibrating it to measure up with what we now know?
Okay, I think I can answer a series of questions based on what you were asking about. So one is that initially what were published were what you might call relative personal equations. And I believe that the standard practice was it was relativized to the head of the observatory. So how you differ from the, I don't know if this was universal, but I believe that it was fairly common to be done that way. Once you had the galvanic chronometer, then what you could do is you could compare your eye and ear method observations with what the chronometer gave you, and then you could get what was called an absolute personal equation. And because the chronometers were so expensive, people could take that information and they would compute this once a year. It's kind of like a Mormon, you get your temple admit card renewed once a year sort of thing. They would go out and they would use that personal equation and they would take all kinds of observations with the eye and ear method, and they'd be able to normalize them back to a standard value later on. So there were two different stages of sort of use of the personal equation in the 19th century. I don't know about the going back business except to say that, I mean, that's essentially what Bessel was doing with Mascaline and Kinnebrook. And I believe that this sort of thing has always been done to some degree, like you're sort of doing a reduction based on old observations given what you now know. And so I don't know how explicitly that was done to sort of calibrate some ancient astronomer's personal equation. I don't think that was really the reason people did it, but certainly that sort of thing was done. Okay?
So I guess I'm just sort of curious, looking back, knowing what we know now about how to calibrate this stuff, how much can we account for Kinnebrook's error? I know you suggested the story's more complicated than what Bessel wanted to say, but like we're getting close to a second of error, which seems massive, right?
Yeah, and in fact, the difference between Wahlbeck and Bessel was over a second.
Right.
And so from the numbers I remember seeing, and they'd show like various tables from different observatories, those numbers were not out of range. They were among the highest, but you would find things on the order of 0.2 of a second and up, quite frequently. So, but it would be interesting to take a closer look at all of that. In fact, the Nature article is mainly about kind of the relationship between Kinnebrook and Mascaline, and then they throw out these sort of tantalizing histograms showing all this data analysis that they don't actually include in a detailed sort of account of in the piece. So that would be an interesting thing to look at.
Sorry, this is cumbersome.
Something that your talk kind of reminded me of was how in criminal law, eyewitness accounts are considered to be very inaccurate and untrustworthy because you'll have several people who see a crime and they'll disagree about the most basic facts about it, which kind of raises the question, if we don't know what's real, how can we trust reality? So my question is I do have a question. The personal equation, when this was established, did anyone ever apply it to anything outside of astronomy or just generally science, or was it really limited to that?
Well, yeah, I sort of alluded to this a little bit in some passing remarks, that in general it sort of took lots of other areas of intellectual inquiry by storm. And so William James talked about a personal equation that just had to do with sort of your tastes about what's true in the world or which things that you might like. And so, especially in the Canales book, she has a nice chapter sort of illustrating all of these now forgotten, they're almost like phrenology, kinds of phenomena. There's approaches we might now regard as completely nuts, but they had a big following in the 19th century. People took them very seriously. But I don't know that in a case like that you would have the nicely well-defined sort of observational regime that you could characterize accurately like what you had here. And you actually had, even though you had all these different observatories, you could still have a sort of basically standard way of marking a transit that everybody discussed. Whereas, if you're an eyewitness to a crime, you're typically not expecting to see a crime. You got other things on your mind, and this is a much harder thing to approach. And I know a lot of philosophers will be aware of these studies about memory. A lot of times it comes up about personal identity, that people's memories are outrageously bad, even about things that we think we really know well. So the psychologist Ulrich Neisser in 2001, after the 9/11 attacks, he had surveyed a bunch of people and just asked them, well, what were you doing when you heard about this? And he would record it, and then he asked them 6 months later, and their answers were not anywhere close on average to what they had said. I mean, this is kind of astounding to us. And we'd all say, well, I know where I was, but the other 60% of people are a bunch of dopes. They can't remember anything. But it's statistical. So, we're probably in that same 60% in that regard. So that's an area that I know psychologists have studied quite a bit, but I don't know that it intersects quite that germanely with personal equation. So.
Then it's you, I know.
Well, then David, then.
No, okay. So I'm curious, here's a man, Bessel, who has interest in having answers. And it just seems as if he's left the concept of constant and voluntary differences hanging without really exploring why, where, and how. Is that a result of my not knowing enough about Bessel, or was Bessel someone who was content to just find this concept and let it sit?
I think the latter is exactly right. I mean, that's exactly how I've tried to present it, and it seems that the record of what he wrote and left behind is consistent with that. It was sort of like, well, here's sort of a solution. We have, this is not due to just sloppiness of measurement. We have to keep this in mind. We have to know that there's a sort of a tolerance beyond which we can't go with our precision, and we'll sort of leave it at that. And he lets other people settle the whole matter. One thing I'd be interested to look at is, I mentioned that John Pond came up with the notion of the personal equation. At this time, so thinking of a piece by Simon Schaefer, he talks about how at the end of the 18th century there were 5 people working in the Royal Observatory. At the end of the 19th century there were 55. And so suddenly you have this problem of trying to manage a workforce. And I believe at Königsberg that there wasn't much of a workforce throughout Bessel's lifetime, and so he may not have had this problem of managing a whole bunch of people forced upon him in the way that Pond did. So that might account for why he didn't care that much about it. It was a matter of, kind of normalizing observational reports between his colleagues who ran other observatories and so forth that he was concerned with. He wasn't concerned about running a whole big observatory and producing almanacs for the Bureau of Longitudes. So
Curiosity wasn't piqued.
well, I'm not entirely sure about the details there, but I think that's a good conjecture as to why he might not have cared as much as other people did. Okay? I always appreciate your questions, Marianne. I always know where you're coming from and how you and I don't agree about things, but I always like to hear it.
So, can you hang on to yours for a second? Because mine kind of follows on Marianne's kind of, I think, neatly. So maybe. So I'm really interested in 2 pieces of this that I want to kind of just maybe it's a combination suggestion question. One piece is the thing you mentioned very early in the talk about how Mascaline sort of presumes that he is the head of the observatory, is the sort of standard of measurement, and then this actually gets sort of institutionalized for a while, or instituted for a while as the sort of standard way of publishing personal equations when they actually start to get published. So question number 1, I guess, is how are we thinking about the difference between a kind of, model of accuracy that's hierarchical versus a model of accuracy that's using some other kind of structure for thinking about what counts as objective truth here, Right. I mean, this is sort of, it's very interesting because it seems like there's something about, there's a kind of elitism, but we can't necessarily make it correlate to objectivity, or we're not sure if we can do that, right? So I guess I'm thinking about the institutional structure there, and then I think that dovetails with some of what you said in relation to Marianne, right? How much of what is and is not a problem here is determined by, again, it seems like institutional imperatives. Both don't rock the boat too much, don't make what we're doing seem like it really has no foundation at all, right? Manage the problem as quietly as possible, a series of other things, right? So I mean, I guess I wonder, I mean, I think there's something really interesting to think about here in terms of, how what's an acceptable amount of error is getting defined in relation to a series of things that may very well not have a whole lot to do with science so much as with its institutional place in the world, if that makes sense.
Yeah.
All right, so I'll stop there. But
Yeah, so the piece by Schaefer, it's called Astronomer's Mark Time, definitely gives this kind of sort of a Latourian analysis of what's going on. I think he sort of assumes lots of things that don't have a great deal of support, but he claims that this is sort of provides a means to have an army of highly controlled menials in the observatory, and that he mentions that it's almost like a panopticon, like every little thing they're doing is getting excessively scrutinized and checked, and they're getting uprated for it and so forth. And there's certainly some truth to that as a development, but I don't think that it explains how the resolution comes about, because the resolution isn't merely that. It actually is a way of, it provides a means to normalize the data in the end, and that's an accomplishment that seems to be outside of social hierarchies. Right. That seems to be a fact about the world that they've created. But yeah, there's certainly a great deal there. I mean, there's certainly a lot of sort of interesting social history that goes on with these stories. I mean, apparently Mascaline was somebody who went through assistance at a very high clip because he was really a pain to work for. So, not surprising. Did I answer?
No, I think so. I mean, I wasn't. I mean, I was just thinking about what I was trying to get at was less. I mean, partly yes, this sort of social hierarchy stuff, but partly the way in which that impacts with. And not just that, but I guess maybe also the practical need for this data to be perceived as reliable, and indeed to be reliable to a certain degree of functionality, right? So I mean, we have to make it work for what we want it to work for, but then we also have to have people kind of believe that it's reliable, right? So there seems to be a sort of series of the rhetoric of whether we kind of dig into this problem and make it into a thing or not seems to be governed by some of that.
Yeah, and I guess I could comment on that too, that I don't know enough about the social context of all of these different observatories to know how it worked at each of them, nor do I know that it was consistent from, say, the Royal Observatory to Königsberg and so forth. I mean, they might have had very different sorts of institutional priorities that they were working under. I don't know enough about that.
I mean, that's part of what I was sort of thinking, is that might be an angle to look at. But anyway, here, David.
So I'm curious as to what developments may have occurred in cognitive psychology and brain science to account for the actual differences. Because it strikes me that it's all sorts of reasons why different observers are biased in different ways. And there's a kind of a layered, mixed up hierarchy of levels of interference that we're all familiar with if we've thought about philosophy of science at all, including theory infecting observation and thinking and trying to produce results that you think your boss will like. But it doesn't sound like this is any of those things. And if it were different instruments making the observations, what we'd do is calibrate the instruments so that they ended up in the same way and figure out some way of that we thought was accurate for the instrument to be doing the measurement. And it sounds like the instruments are just operating in different ways. And that seems to be true. I mean, I'm a pretty uncoordinated guy. I'm, always the last guy at the low end of the bell curve. If we're trying to learn physical movements, I'll learn them last. And I'm not very good at catching balls or hitting things with rackets or anything like that. And I come to understand, from what I can tell, that's not about how fast the nerve impulses travel, though that's a little bit of a difference. It's also something about perception, how you see things around you. But it strikes me that there seems to be a regular difference in these people as to how fast, is this it? How fast they perceive things, or something of that kind. And has anybody studied that and tried to use these data to help them understand or get a curve for differences in people or something like that?
To answer your questions, kind of embarrassedly, I'd say I really don't know much about what contemporary psychology makes of this problem. But I'll say in my defense that it usually occurs in these articles and researches as kind of a settled fact that gives us a model of how we might look at other facts that aren't yet settled. And especially in the psychological writings, people would indicate that Wundt and Helmholtz sort of settled all of this by giving us kind of a picture of how long it takes for nerves to make their transmissions. And people talk about how this was during the period when telegraphs were getting put up all over the place and people were aware of all of these practical problems there, and they sort of analogically moved to looking at us in this kind of way. But all of that is kind of a hand-wavy story to me. And as I read more and more about this, I was kind of frustrated because the writers would always indicate, like, well, this is the personal equation, and we all know what happened there, right? I'm like, well, I don't know what happened there. And I feel like that there's a strange tendency in this to act as though the problem is already settled and well understood, that you don't find in other areas. So I don't know what kind of sort of exploratory research would be done in contemporary psychology on this question. And at various points, I felt kind of stupid as I was reading this stuff, because I felt like, well, there's got to be something that I should know that everybody else seems to know. And then after I read enough about it, I thought, well, no, they're just all pretending they know stuff that they don't, apparently. I don't know. I mean, I guess that's a self-aggrandizing belief to have about the reasons. But it did seem like that void was throughout the literature. So probably the best article I read about it was from 1888 by E.C. Sanford. It gave the most complete description of all of the ins and outs of the observations, and that was all in terms of 1880s psychology. That was probably the one that came the closest to actually coming to grips with psychological mechanisms, but it didn't come that close. Okay, I think Mike has a...
So maybe I'm making too much of this, but start to worry about things like, our ability to replicate results, especially in things like social psychology experiments. And obviously there can be a huge problem in terms of, okay, is the experiment actually designed in the same way? I mean, is there some fundamental difference in how you're actually applying the treatments or something like that? But then I start to wonder in these sorts of ways, I mean, is it that I'm seeing differences in the results because you perceive people as being 20% less happy than I do, right? I mean, are there perceptual differences then in terms of how I am interpreting the results that I'm seeing, right? In the same sort, I mean, to me, it's feeling like it's the same sort of thing. I mean, you're not then having the same sort of mechanistic observations that you're making, and so it becomes a little more nebulous in terms of trying to put a personal equation on it, but effectively that's potentially happening, isn't it? I mean,
well, I think if I could sort of reconstruct your worry, it might be something like either we're all kind of seeing the same thing and we're getting the same data in, and then we're sort of messing with it and getting it wrong in a characteristic way. I mean, that's a picture that I think we would all like a little bit better, because it means the world is the same to all of us. The picture that I was arguing for was that on the phenomenological level, these things seem to have been different. They would have looked different through one person's eyes than somebody else's. And the idea that there was the wrong interpretation put on it doesn't seem to be anything you can find. And the reason it was so hard to grasp was everybody would think, well, I looked and I saw this thing moving and I saw exactly when it crossed the line. And it didn't match up with what other people had said. So those are two distinct ways to understand it, and I'm thinking that the second way is actually the right way, although I don't know because I can't see anything from anybody else's perspective.
But I guess,
But-
okay. Because I think it gets back there to the eyewitness account sort of issue of, it's like we are watching the same thing, right? And so if I could see it in the same way that you're seeing it, maybe I'm falling back into that same question then, so never mind.
Well, I'd like to answer your.
What's that?
I hate to be that guy.
Well,
I'm going to let Matt say the last thing he has to say to Mike, but then we're going to have to cut it. We're actually out of time.
okay. No, I think we can talk about it afterwards and figure out.
So let me just thank Professor Rowan.